Hello everyone. Now in this lecture we are going to see the mathematical deduction of Wien's displacement law. We will do this by using Planck's distribution law. Particularly why Wien's displacement law is necessary because it tells us about the wavelength for a particular temperature, the wavelength at which the body will emit the maximum amount of radiation or its emissive power will be maximum, and that is why deduction of this law in a mathematical form is necessary. It gives us a relationship, it gives us a direct relationship between the wavelength corresponding to the maximum emissive power at a particular temperature of that body, and that's why this is important. So let us proceed for this using Planck's distribution law. So firstly we need to understand that emissive power changes with temperature, and if the temperature is constant or we consider a particular temperature, then emissive power also changes with respect to wavelength. And hence, to deduce this law, we have to differentiate the emissive power, that is, let us say the emissive power of a black body, which is a function of wavelength, and that's why EB means emissive power of the black body, and the suffix lambda means it is dependent on wavelength. This term we need to differentiate with respect to wavelength itself and then equate the outcome to 0. Now, how do we see that? This emissive power of the black body using Planck's distribution law, it can be directly written as, now this d by d lambda is simply the differentiation with respect to the wavelength. So d by d lambda of C1 lambda raised to minus 5 divided by exponential of the entire quantity C2 by lambda t minus 1. This differentiation of this entire quantity with respect to wavelength lambda should be equated to 0. And then we can find out the relationship between lambda for the maximum emissive power and the temperature T. So now we will proceed with the differentiation. We observe that in the numerator, this term C1 lambda raised to minus 5 involves a term of lambda, so its differentiation will be done. In the denominator, the term of exponential of the quantity C2 by lambda t involves a term of lambda. So that's why its differentiation will also be done. So let us proceed. Firstly, we will differentiate only the numerator, then we will differentiate the denominator. So for the numerator, we simply have, because C1 is a constant, so C1 as it is, multiplied by, we know that differentiation of, let us say there is some parameter such as, let us say, x raised to n, then its differentiation will be n multiplied by x raised to n minus 1. So similar to that, differentiation of lambda raised to minus 5 will be minus 5 multiplied by lambda raised to minus 6. This we know from the basics, divided by the same term exponential of C2 by lambda t minus 1. This will be the whole denominator. Now we have differentiated the numerator. Now we need to differentiate the denominator. In the denominator, this is the term which is related with lambda. So that's why firstly we will see what will be its differentiation. This entire term, it can be considered as x, and as we know, differentiation of 1 upon x is nothing but minus 1 upon x square. So simply we will write it like that. So that will be minus 1 upon x square, which means minus 1 upon exponential of C2 by lambda t minus 1 entire bracket square. Then the numerator will remain as it is, that will be C1 lambda raised to minus 5. And then also we need to differentiate this exponential parameter entirely. So differentiation of this exponential will be again exponential, because we know that d by dx of e raised to x is nothing but e raised to x multiplied by d by dx of x. And because in this case d by dx of x is 1, so we generally consider it to be e raised to x. But this will not be the case in this scenario. So we'll have to calculate the first this differentiation as well as the second differentiation as well. So firstly, differentiation of this exponential of c2 by lambda t will be simply exponential of the term c2 by lambda t. Differentiation of this minus 1 will be 0, so no need to write it there. And then multiplied by, we will also need to write differentiation of this c2 by lambda t. Like I said, there will also be one more differentiation for only x. So in this case c2 and t both are constants, so that's why their differentiation will not take place. On the other hand, 1 upon lambda is the term for which differentiation will happen. So again, differentiation of 1 upon lambda will be minus 1 upon lambda square. So you will get c2 upon lambda square t, and this will be minus c2 upon lambda square t. And then this entire quantity should be equated to 0. So now we will need to equalize the denominators of both the terms so that we can proceed with further mathematics. So we will multiply the first term, because here it is the square of this entire bracket. So we will multiply the first term with multiply and divide actually with exponential of c2 by lambda t minus 1, this entire bracket. And so that in the denominator these both the terms will have a same term. So that's why what we will do now, when we multiply and divide, we get minus c1 lambda raised to minus 6 multiplied by exponential of c2 by lambda t minus 1. And actually the denominator has now become common, so I will simply write it only once. So the denominator will be exponential of c2 by lambda t minus 1 bracket squared. Okay, and now in the numerator the same term, no change with that. Actually only the change will be this negative and this negative, they will cancel out each other, so it will become positive. So plus c1 lambda raised to minus 5 multiplied by exponential of c2 by lambda t multiplied by c2 by lambda square t, and this entire thing should be equal to 0. Now what we can do, we can directly take this on the other side and multiply it to 0, so denominator will be eliminated. What remains with us is this entire term. Now in this case we can multiply this minus 5c1 lambda raised to minus 6 inside the bracket. So what do we get? So we get by simplifying the terms, so that we can reduce the terms actually. So it will be minus 5 c1 lambda raised to minus 6. So multiply it with the first term. So at that point we do get minus 5 c1 lambda raised to minus 6 multiplied by exponential of c2 by lambda t, the first term. Now the second term is minus 1, so this minus and this minus will become plus. So plus 5 c1 lambda raised to minus 6, finished with the first bracket or the first term, and the second term will be c1 lambda raised to minus 5 and then exponential of c2 by lambda t multiplied by the whole term c2 by lambda square t. This should be entirely equal to 0. All right, now next thing, we observe that in the first term as well as in the second term, this 5c1 lambda raised to minus 6 is a common parameter. Also there is something called as c1 lambda raised to minus 5 in the second term. So we will divide the entire equation by 5c1 lambda raised to minus 6. Just 5c1 lambda raised to minus 6 and not the negative sign. We will not take the negative sign in this case. So divide this by 5c1, let us say I have divided this by minus 5c1 lambda raised to minus 6. So this will become only minus 1, so minus exponential of c2 by lambda t. This is already positive, so this will be only plus 1 because I am dividing it by 5c1 lambda raised to minus 6. So entirely numerator and denominator will cancel each other. Plus, now in this case we are dividing it by 5 c1 lambda raised to minus 6. So c1 will be absorbed. I will just write it over here in simple terms. So 5 c1 lambda raised to minus 6. So now what we see over here, c1 will absorb each other, okay, then 5 will be in the denominator afterwards. Now actually from this 1 lambda will be remaining, which can go, because 1 lambda will be remaining, which can be multiplied over here. So lambda raised to minus 1 can be multiplied at this point. So this is lambda square, this is lambda raised to minus 1. When they are multiplied with each other, so only 1 lambda will remain, and this lambda raised to minus 5 and this lambda raised to minus 5 from numerator and denominator will be absorbed. So that gives you plus exponential of c2 by lambda t first term multiplied by, here only 1 lambda will remain, so that will be c2 by lambda t, and also this 5, it does not have any cancellation other parameter available, so this will be over here. So you will see this should be equal to 0. So ultimately we see that there is c2 by lambda t over here, there is c2 by lambda t here, and c2 by lambda t at this point. So we will assume that this c2 by lambda t is equal to x. So by this assumption we can rewrite this entire equation. So it gives us minus exponential of x, because this is the entire thing that we have considered as x, plus 1 plus. Actually this will be exponential of x multiplied by x upon 5, because c2 by lambda t is again x, and this will be entirely equal to 0. Now this is a transcendental equation. I will write the spelling here for you. So this is a transcendental equation, and because it involves so many terms such as this exponential term and other algebraic terms, and this can be solved using trial and error method or numerical method. So we will solve it by trial and error method. Now I will show you how to do that if you are doing such equation on a calculator. So firstly I will have to put this entire equation inside the calculator. So let us see how to do it. So hold on a second. So this will be actually minus, my mistake. So minus exponential of x plus 1 plus exponential of x into x upon 5. So that's why exponential of x into x upon 5, and then we will press the calc button because we have to do this multiple times. So we will first press the calc button. So let us say we put the value of 1, so we get some negative value minus 1.17. Let us say we put 2, minus 3.43, negative is increasing. We put 3, again negative is increasing. Then we put 4, then we see negative is still increasing. We put now 5, we see that we have got some positive value. So between negative and positive there will be one 0 value. So between 4 and 5 there will be one answer. So I will put 4.5 equal to, so that gives us minus 8. Remember at 4 it was minus 9, but now it is only minus 8. So I will go further ahead. Let us say 4.6. Okay, so from minus 8 it has reduced, actually it has improved to minus 6.95. So I will directly jump to, let us say, 4.8 minus 3.86. Now I am still moving towards the 0. So 4.9. Okay, good. And at 5 I know it is going to be 1, so there is no point in writing 1 now. So I will put 4.95. Okay, I am still moving towards 0. So 4.96. Okay, 0.14, and 4.97 is actually 0.13, again positive. So again between 4.96 and 4.97 there is a 0. So 4.965 I'm writing. So what do I get? I get minus 3.15, but into 10 raised to the power minus 3. So that is 0.003. So this is as good as 0. So now what I can do, I can write the value or the solution for this transcendental equation by trial and error, that by trial and error when we solve it, we get x is equal to 4.965. If you want, you can see the calculation procedure once again by rewinding the video, because it is very necessary for you to understand this. If this is 4.965, then what exactly is x? X is nothing but C2 by lambda t, and it is equal to 4.965. So now what I will do, I will substitute the value of C2, which is already known to me. Also, I will make one change over here. Afterwards, we will not call this lambda as just lambda. We will call it as lambda max, which means the wavelength corresponding to the maximum emissive power or maximum radiation from that particular body at that particular temperature. So let us see. We will now do what we will do. We will substitute the value of C2 now. Okay, so I will write it once again. So C2 upon, actually this will be lambda max into T. It will be equal to 4.965. Alright, now we will substitute the value of C2, which is 1.438 into 10 raised to 4 divided by lambda max into T. It is equal to 4.965. Remember once again that we are doing all this mathematical treatment to find out the relationship between lambda max and T. So we will take this entire denominator on the other side. So let us see now. So it means that this lambda max into T is equal to 1.438 into 10 raised to 4 divided by 4.965. So let us do the math. So 1.438 E4 divided by 4.965. What we get is 2897 approximately. 2896.27. Generally it is taken as 2897 considering errors in the decimal places, because we have solved the equation using trial and error method. So ultimately it means that the conclusion is lambda max multiplied by T is equal to 2897. Now what will be the unit of this quantity 2897? Unit of lambda max is a micron or a micrometer, and unit of temperature will be Kelvin, so that will be micrometer Kelvin. So this will be your mathematical deduction of Wien's displacement law. Now what is the physical significance of this? Remember, the number that we have got is a constant number. It means that if the wavelength changes, then the temperature at which the maximum emissive power, or my mistake, actually at a particular temperature, the wavelength at which maximum emissive power will be given by a body will change according to this number. As you increase the temperature, wavelength will actually decrease. So more and more radiation will be emitted by a higher temperature body at lower wavelength. That's the physical significance of this relation. Also, it helps you to calculate the wavelength at which maximum emissive power can be obtained when you know the temperature of operation of that body. And that's why this mathematical relation is important. I hope this is useful to you. Thank you.